Welcome to Unit 8, Lines and Planes, Lesson 4, Intersections of Lines in Space, in 2 space and 3 space. Really, Lesson 4a was dealing with 2 space, so today we're really going to focus on 3 space. However, I will talk briefly about 2 space. Lines in 2 space can have as follows: no, one, or infinite solutions. So there we go. Let's move on to 3 space. So 3 space, same thing. It can have if they are distinct, which means they're not the same, and intersect at a point, so there's one solution. So for instance, here we go. This guy right there, there's a point of intersection. Alright, these lines are collinear. One line is on top of the other, so that there are infinitely many solutions. The lines are parallel, however, there's one on top of the other, so they actually share the same line. The third one is parallel and distinct, so there are no solutions. These lines never meet. And then finally, number 4, so this is new. 1, 2, and 3 are basically just what we saw in 2 space, but number 4 is new. The lines are distinct, not parallel, but they do not intersect. The best way I like to look at this is this: you take 2 rulers, you put them so they pass each other, but they do not touch, and they're not parallel. Those would be called, they would not have a solution. These are called skew lines, and they do not have a solution, so there's no solution here. Alright, so this number 4 is new, and again, keyword here is skew lines. Okay, let's continue. To determine if 2 lines in 3 space intersect, the first thing you always want to do is look at the direction vectors. And so here my direction vector for line 1 and my direction vector for line 2, I can see that if I multiply my direction vector for line 1 by 2, I will get the direction vector from line 2. So what does this mean? This means they are parallel. Well, how does that help us, Mr. Wills? Well, if they're parallel, they will either be collinear or they will be parallel and distinct, so we have to check that out. How do I check it out? So what I do for this is I take a point from line 1 and put it into line 2. So I'm going to have, here's line 2. You could do it vice versa. You could take the point from line 2 and put it in line 1 and check if it works. But we're going to do line 2 here. So I'm going to have, so again, this guy goes in for x, y, and z. So I'm going to have 4, 1, 5 is equal to -2, 16, and 2 plus t, 4, -10, and 2. Now what I'm going to do is equate the x's, the y's, and the z's. So if I equate the x's, here's my x's, I'm going to have 4 equals -2 plus 4t. Bring this guy over, I get 6 equals 4t. So t is equal to 3 over 2. Alright, there's the first one. Now I'm going to do y's. So my y is the middle coordinate, so 1 is equal to 16 minus 10t. Bring this 16 over, I get -15 is equal to -10t. Divide both sides by -10, I get 3 over 2 is equal to t. So far so good. So if the last one, if coordinate z is also equal to, if t is equal to 3 over 2, that means that they are going to be collinear and have infinite number of solutions. If t is not equal to 3 over 2, then they'll have no solutions, be parallel and distinct. So here we go. I'm going to have 2 is equal to, or sorry, not 2. My mistake. Is going to be 5 is equal to 2 plus 2t. So bring over the 2, so I get 3 is equal to 2t, and here I get 3 over 2 is equal to t. What does this mean? Well, look at this, I got this, this, and this. They're all the same. So what does that mean? Therefore, the lines are collinear, which means they have, therefore, infinitely many solutions. Alright, there's example 1a. Let's go to 1b. So 1b, I'm going to just scratch this out because I've already done this video once and I started to use lines from both of them. So I'm just going to remind myself, do not use this one. Alright, there we go. So I can see here, if I look at the direction vectors of both lines, I can see they're not scalars. If I multiply this by 6, I would get, or sorry, multiply this one by 6, I get this, but if I multiply this one by 6, I do not get this, so they're not scalars. So step 1 is I check for the scalars, and here I can see that m1 is not equal to some scalar of m2, so they are not parallel. Alright, what does that mean, Mr. Wills? Well, that means I've got two cases I can look at. I can either look at skew lines, or I can look at they intersect. So here we go. Let's go over here. The first thing I want to do after I find that they're not parallel is I want to write them as parametric form. So I'm going to cheat a little bit. If you want to know how to do that, again, go to lesson 1. Okay, so I've got them, and what I'm going to do is equate the x, y's, and z's. So let's do this. I'm going to equate the x's. So for my x's, I'm going to have 4 plus s is equal to 8 plus 6t. Bring everything over. Actually, I'm going to isolate for s here. Why? Because if I isolate for a variable, this might be helpful later on. So there's my x's. Let's go to y's. So y. So I'm going to have 2 minus 4s is equal to 1 minus 9t. If I bring everything to one side, or I'll keep the constants on one side, variables on the other side. Here I'm going to have 9t minus 4s is equal to negative 1. What can I do with this? Well, I can actually take this guy here, this s, and put it in here and solve. What will that do? Well, I can solve for s, or sorry, then I can solve for t, and then I can solve for s. So let's do that. So here we go. I'm going to take, again, from x and y, and I'm going to have this. I'm going to have 9t minus 4 times 4 plus 6t equals negative 1. 9t minus 16 minus 24t is equal to negative 1. And we're going to get on this side 15. On this side I get negative 15t. So here I can see t is equal to negative 1. Alright, and now I also know from my equation from x, I can solve for s. So then I know that s is equal to 4 plus 6 times negative 1. So s is equal to negative 2. So I have got my t, I've got my s. What do I do now? Well, I haven't looked at my z's yet. So what I'm going to do is plug in s and t into z and check if it works. If it works, if left side equals right side, there's a point of intersection. If left side doesn't equal right side, there's no point of intersection. So here we go. I'm going to look at z now. So z is 1 plus 5s equals negative 14 minus 5t. Plug in this, so I get 1 plus 5 times negative 2 is equal to negative 14 minus 5 times and negative 1. So here I'm going to get 1 minus 10 is negative 9 equals, over here I'm going to get negative 14 plus 5 is negative 9. So this is true. Woohoo! So that means, therefore, there is a POI. What is that POI? Well, I'm going to take this, substitute it into either my line 1 or line 2, and I'm going to solve for the point of intersection. So let's go with, I like working with negative 1 a little bit easier, so I'm going to go with line 2. So line 2 tells me this. Line 2 tells me that x is equal to, whoops, line 2 tells me that x is equal to 8 plus 6 times negative 1. So here x is equal to 2. Y is equal to 1 minus 9 times negative 1. So here y is equal to, that's going to be plus, so it's going to be 10. And then finally z is equal to negative 14 minus 5 times negative 1. So it looks like y is equal to negative 9. Therefore, the POI is 2, 10, negative 9. So I had to check first. Once I find that it's true, I plug it into one of my lines, either s either t into line 2 or s into line 1, and I found it, and I got my point of intersection. By the way, that is a 9, not a whatever number it looks like there. All right, let's continue. Last one, example 2. Well, not the last example, but the middle example. Determine if they're skew. So here we go. To determine if they're skew, what we're going to do here is, again, go to the parametric form. So there are my two parametric forms. And I do the exact same thing I did just before. So if you want to fast forward through this, please be my guest. But again, we look at the x's. So x here will be 5 plus s is equal to 2 plus 2t. I can isolate for s pretty quickly here. So I get s is equal to 2t minus 3. And then for my y's, I have here negative 4 plus 2s is equal to negative t. Well, that's nice. So what can I do here? It's going to plug this in. So I have negative 4 plus 2 times 2t minus 3 equals negative t. So if I do this quickly, negative 4 plus 4t minus 6 is equal to negative t. Let's see here. So if I bring these over, so I get a positive 10 on this side, here I get a 5t. 5t is equal to 10. So here t is equal to 2. Alright, I got t is equal to 2. Beautiful. Let's continue. So if t is equal to 2, then I can get s. I'll just continue along down here. S is equal to 2 times 2 minus 3. So that means s is equal to 1. Alright, so I've got my s and t. So now I'm going to check this in z. So here we go. Z is equal to 2 plus 3s is equal to 1 minus t. Plug in what my left side, right side. So 2 plus 3 times 1 is equal to 1 minus 2. So here I get 5 is equal to negative 1. What the heck, Mr. Wills? That's not true. Definitely not true. Therefore, the lines are skew. No POI. By the way, one thing I forgot, again, first check this, check the direction vectors to make sure that they're not scalars of each other. I can clearly see these are not scalars. If I multiply this by 2, I get this guy. If I multiply this by 2, I definitely don't get this guy. So that quick check of the scalars, there we go. But I can see that these two lines never intersect, because when I solve for s and t and x and y, it doesn't work in z. Alright, last one, promised this time. Here we go. So this one, determine the distance between the skew lines. We have shown these are skew. By the way, this is from example 2. These two lines are skew from example 2. It says here, when asked for the distance, the question really implies, because there's infinitely many distances between skew lines, it's really asking for the shortest distance. Recall from grade 10 math, the shortest distance between a point and a line is the length of the perpendicular from the point to the line. So what does that mean, Mr. Wills? That means, here's my point in grade 10, here's my line. It would be something like this. This line that I'm drawing right there, if it is perpendicular, is the shortest distance. So when I ask for really the distance, I'm really asking for the shortest distance. The shortest distance between two skewed lines is the length of the common, and here we go. Is the length of the common perpendicular. Again, from grade 10 math. But here in grade 10 math, it was really 2 space. Here we're in 3 space, so a little more complicated. Here we go. So this is my diagram here. So here we go. I've got point 1, point 2. Let me just point 1, point 2, and then here I've got this guy here. Now this right here is the shortest distance, this AB. But I got to figure it out. I got to figure out that distance there. So how do I do that? Ultimately, what we want to do is we want to find the projection of P1, P2 onto the normal, which this is what this guy is right here. This is the, I want to find the projection of this onto this. Okay, but how do we get the vector AB? Well, AB is perpendicular to both L1 and L2, so that to determine the AB, we need to calculate the cross product. of the direction vector of M1 and M2. So if I get the direction vector of the line 1, direction vector of line 2, and do the cross product, I'll get a line that's perpendicular to both L1 and L2, which is actually will be my AB. From lesson 3, we know this as the normal. All right. So, just to recall, sorry, I'm just going to fix this. Bring these back here. So to recall here, the formula for the magnitude of the projection of u onto v is this. Magnitude of u dot v over magnitude of, and this is actually incorrect. It should be the magnitude of, not u, but v. All right. Therefore, the shortest distance between two skew lines is this. The magnitude of the projection of P1, P2 onto the normal, which is actually equal to the magnitude of P1, P2 dotted with the normal all over the magnitude of the normal. Oops, the normal. There we go. So that's how I get the shortest distance between two skew lines. So step 1, I want to find the normal. The normal will be M1 cross M2. So here we go, I'm going to write it out. 1, 2, 3, 1, 2, 3, and 2, negative 1, negative 1, 2, negative 1, negative 1. There we go. So it will be negative 2 plus 3. So the normal will be negative 2 plus 3, comma. For the next one, here I'm going to have 6 minus 1, or 6 plus 1, sorry, comma. And the last one I'm going to have is this. I'm going to have negative 1 minus 4. And so my normal will be 1, 7, and negative 5. So I have the normal. What else do I need to find? I also need to find P1, P2. P1, P2 is pretty easy. I'm just going to take these guys and find the direction vector between those 2 points. So here we go. I'm going to have 2 minus 5, 0 plus 4, double negative, and finally 1 minus 2. So it's going to be equal to negative 3, 4, and negative 1. Alright, so now I'm ready to use my formula. I'm just going to extend this page a little bit. Hope you don't mind. So the shortest distance between the 2 points is this. I'm not going to write this formula again, but it's going to be equal to the dot product of these two. So it's going to be on top here. I'm going to have 1 dotted with negative 3, or multiple by negative 3, plus 7 times 4 plus negative 5 times negative 1. All over the magnitude of the normal. So here we go. I'm going to have 1 squared plus 7 squared plus negative 5 squared. So on top, on the numerator, I'm going to cheat a little bit, 30, negative 3 plus 28 plus 5. All in the denominator, I'm going to have the square root of 75. So this is equal to, if I want to go to decimals, it's going to be about 3.46. Therefore, the distance between line 1 and line 2 is about 3.46 units. And again, it is the shortest distance. Thank you for listening to Lesson 4.